We've kind of dived into a new topic of separable differential equations. When we're talking about differential equations, there are only two things that I need to have to make something a differential equation. It has to have an equal sign. That's what makes it an equation. And there's got to be a derivative in it somewhere. And that's what makes it a differential equation. So I need an equation and some kind of derivative. Now the derivative can show up anywhere in the equation. It can be on the left-hand side, it can be on the right-hand side. It doesn't have to be isolated on its own, but in order for something to be a differential equation, it's got to have a derivative and an equal sign. So when we talk about solving a differential equation, that usually means we're going to have to do something to get rid of the derivative and take some sort of antiderivative. A couple other there's some vocabulary stuff that comes along with differential equations. Another thing to note here, whatever variable is like in the numerator on top in my derivative term, that's my dependent variable. And whatever variable is on the bottom, that's my independent variable. If I look at the other side of this equation and it only involves my independent variable only, we call this pure time. We call it a pure time differential equation. Even if the variable isn't t, we still often refer to it as a pure time differential equation if it only involves the independent variable. Now, these are kind of the most straightforward because this is what we've been doing for a lot of last quarter. This just tells me to find the antiderivative. So solving this equation comes down to me finding the antiderivative. Antiderivative of 3x squared is x cubed. Antiderivative of e to the x is e to the x. Just like in 19b, when I take that antiderivative, I really have a family of antiderivatives with some sort of plus c constant. And if I've been given more information in the problem, I can solve for what that constant is. So for example, if I knew that when y equals 4, or rather when x equals 0, y equals 4, that's enough information for me to solve explicitly for that differential equation, to solve explicitly that differential equation, including a value for the constant. So in this case, it looks like if -1 plus c has to equal 4, then that means c is equal to 5. And I would say that the solution to the initial value problem is that y of x is equal to x cubed minus e to the x plus 5. So my solution to the initial value problem should include the value of that constant c. Something like dy dx is equal to 3y. It's a differential equation because I have an equal sign and a derivative. But this time, my dependent variable is the variable that appears in my equation. So we refer to these as autonomous. When we have an autonomous differential equation, we have to do just a little bit more work to actually solve that differential equation. And sometimes, which I think is what y'all are going to be talking about in lecture today, We'll have other tools to analyze and investigate autonomous differential equations that don't always involve explicitly solving them. But for right now, the ones I put on the sheet, we can actually explicitly solve for. But to do that, we have to do a little bit of algebra first. And that's why we call these separable, because what we're actually going to do is like separate the y's to one side and the x's to the other side. So in this case, starting with my dy dx, I'm going to divide both sides by y. And I'm going to multiply both sides by dx. And what that's going to leave me with is a super straightforward thing on the right-hand side. And my left-hand side is going to look like 1 over y dy. So this is now in a differential form. And I've got my y's on one side and my x's on the other, or my independent variable on one side, my dependent variable on the other side. And I can find the antiderivative of both sides by taking the integral. So if I integrate 1 over y dy, I'm going to end up with natural log of the absolute value of y. And over here on the right-hand side, I'll end up with 3x plus some sort of constant. Now, if we were given initial conditions, then we would be able to solve for that constant. Just one quick note on that absolute value of y piece. I'm going to go ahead and rearrange this equation to solve for y. Because there's a really common algebra trick that we do with problems that look like this. And it's sort of how we're going to handle that absolute value piece. Good morning. Here. Have one of these. I'm on the second page. So if I wanted to get the y by itself, I know that I'm going to have to switch this from a log equation to an exponential equation. So I'm going to have to make it like e to the stuff. Well, if I do that, then I would have the absolute value of y is equal to e to the 3x plus this constant. Now, the absolute value part means that what's inside could be positive or negative. So how do we handle that? The most common way to handle for this type of problem is that we're actually going to do an algebra trick. It's not really a trick. We are using exponent rules. So if I had something like 2 to the 3 plus 5, yes, that is 2 to the 8th, but that's also 2 to the 3rd times 2 to the 5th, because that exponent rule says if I multiply two things with the same base, it's like adding in the exponents. I'm going to undo that and sort of go from this step back to this step. So up here, I'm going to have the absolute value of y is equal to e to the 3x times e to a constant. The next step is the step that's going to allow me to get rid of that absolute value. Well, e to the constant is just a constant, right? If I knew what that value was in the exponent, I could put that into a calculator. It would spit out a number for me. So I'm going to rewrite e to the c as just some constant. It's not the same c, so if you want to give this a little subscript to indicate that it's not the same c, that's fine. But in so doing, I have now taken care of the fact that that could be positive or negative, and I can drop the absolute value sign on the y. Vocabulary thing, this is autonomous because my variable in the numerator, or my dependent variable, is the only variable that occurs in the equation. So it's autonomous, and to solve it, I have to move my a's to one side to be over here with this differential piece of the dA. So I'm going to multiply both sides by dt. and I'm going to divide both sides by a squared. On the right-hand side, that means I just have a dt. And on the left-hand side, I've got 1 over a squared dA. Once everything is sort of pulled apart and separated, I can use integration to get the antiderivative on both sides. I will give you a minute to do the antiderivatives. So if I'm going to find the antiderivative of 1 over a squared, I really want to think about that as a to the negative 2. I'm going to go ahead and take the integral of the right-hand side. The secret invisible function there is 1. So if I take the antiderivative, I'm going to get back t. It doesn't actually matter which side I put the plus c on. So I usually keep it with the side that's the simplest. Here, if I take that antiderivative, adding 1 to the exponent, I'd have a to the negative 1 divided by negative 1. I don't need to put a constant on both sides, because if I did, they're not the same constant, and if I subtract 1 over and kind of recollect them, I'm still back to just 1 constant. To sort of finish this off and keep going, if I look back to the original differential equation, a was the variable that's my dependent variable, and it's on top. So that's the one that I want to actually solve for and kind of isolate in the equation. So multiplying both sides by negative 1, and then thinking about that a to the negative 1 as really 1 over a. So I would have 1 over a is equal to negative t. And I could write this as minus c. The convention is generally to clean up constants along the way. So we don't have to do that, but you could do that by indicating that this was some constant and then making that, excuse me, making that a plus c. It really doesn't matter which way you do it. Whether you leave that as a minus c or a plus c, I'm just going to leave it as a minus c for now. And if I multiplied by a and divided by this whole piece, I would have 1 over negative t minus c is equal to a, which is now a function of t. So this would be referred to as my general solution, because I wasn't given an initial condition that would allow me to solve for the constant c. A form that looks like I can write my derivative as a function that involves only x times a function that involves only y. Then I'll be able to move my y parts to one side to live with my dy and my x parts to the other side to live with the dx. So let's do a couple of those examples and talk about how to separate pieces. So my first one in this section, I've got e to the x minus y. So at first you might look at that and think that it's not going to be straightforward to separate. But just like we've kind of been practicing in the double integral part, problems that looked like this came up as examples for our double integrals. And one of the tricks to make this a little bit nicer is to kind of undo that exponent rule and write this separately as e to the x times e to the negative y. Or you could even write that as e to the x divided by e to the y. So if I do that, and I'm trying to get my y's on one side, my x's on the other, I can multiply both sides by e to the y and also by dx. And when I do that, I get e to the x dx on this side and e to the y dy on the other side. Integrating both sides this time. Pretty straightforward. E to the y is equal to e to the x plus a constant. Do be careful. If I am trying to solve this to make it say y equals, what do I need to do to both sides? And when I take the natural log of both sides, this side's going to clean up and this side is not because of that plus c. We don't have a log rule for addition inside of logs. That's just what my final answer looks like. Let's give this one a go together. I'm going to just scoot this over a little bit so I've got a little more space to write. So the first thing is to notice that if I have two things multiplied together under a square root, that I can break that apart and call that the square root of x times the square root of y. Can't do that with addition or subtraction, but I can do it with multiplication. Which side did you leave the 2 with the x or did you move it with the y? Okay, so I'm going to leave the 2 with the x. So I'm going to divide both sides by the square root of y. And I'm going to multiply both sides by dx. So I've got 1 over the square root of y dy is equal to 2 square root of x dx. And I'm basically ready to integrate, though I would rewrite both of those to be fraction exponents. So I've got y to the negative 1/2 dy is equal to 2x to the positive 1/2 dx. Adding 1 to the exponent, I've got y to the 1/2. Dividing by 2 is the same as, dividing by 1/2 is the same as multiplying by 2. And over here, I would have 2x to the 3/2 divided by 3/2. And it doesn't really matter which side I put the plus c, but I'll go ahead and put it over there. First thing I'm probably going to do is clean up the fractions a little bit. So I've got 2, and I'm going to rewrite this as the square root of y. And over here, if I divide by 3/2, it's the same as flipping that over and multiplying by 2/3. So I've got 4/3 x to the 3/2 plus a constant. Choices, but I'm going to go ahead and divide both sides by 2. And when I do that, I'm going to say that dividing that constant by 2 is just a new constant. So I would write that as the square root of y is equal to 2/3 x to the 3/2 plus a new constant c. And then to get y by itself, I'm going to square both sides and have 2/3 x to the 3/2 plus c squared.
Can we, what is it called? Square only the 2/3 x and more options.
So we can't because of that plus c, I have to be squaring the entire side. Now, if this were an initial value problem, we could solve for c first. And if c happened to be 0, then I wouldn't have to worry about that, right? But if c is anything other than 0, I have to do the addition first and square that kind of on the outside. Yeah. What do y'all think? Should we dive into some word problem practice? So, Evans price adjusted model. Basic equilibrium price equation sets demand function equal to supply, but when scarcity is a factor, the Evans price adjusted model predicts that at any non-equilibrium price, the change in price will be proportional to the difference in supply and demand. So if I take that phrase and I turn it into a differential equation, the change in price, so I'll just call that dp dx. My change in price is, so I'm going to write an equal sign, proportional to So I need some constant K, the difference in supply and demand. So that means I'm gonna be subtracting supply and demand, right? By the way, why do I know that I should be subtracting the supply from the demand?
What? Why?
Why would I write it as demand minus supply? Fun fact, it doesn't matter at all from an algebra perspective. But the direction that you subtract in will change the constant of proportionality to be a positive or a negative, right? So if something in the problem forced that constant of proportionality to be positive, then if it is a scarcity model, then then I would need my demand to be higher than my supply. So, that's all. But it actually algebraically doesn't matter which way you do it. The constant of proportionality will take care of it. So for this one, I've given us a demand function and a supply function. So we can set this up as our and I guess I give us t as a variable instead of x, sure, whatever. So is proportional to, and our demand function was 5,000 minus 40p, and our supply function is somewhere over here, 3,000 plus 40p. So this happens to be autonomous, which means I know it's going to be separable, but I probably want to do a little work to clean that up before I try to separate it. So I'm looking at dp dt is equal to k times, and then if I distribute that minus sign through, I've got 2,000 minus 80p. And I will give you a minute to separate that and get your integration. I'm just going to divide the whole thing over. So I'm going to set this up as 1 over 2,000 minus 80p dp is equal to k dt. So when I integrate the left-hand side, I know I'm going to have a natural log, but I've got to remember to divide by negative 80. Or if you want, you can do a u substitution on this side. Same result's going to happen. Then I'm going to have a negative 1 over 80 natural log absolute value 2,000 minus 80p. And over here, because I have that constant of proportionality, I'm going to have a kt plus a constant. So if I go ahead and do the algebra to rearrange for p right now, the first thing that I'm going to need to do is multiply both sides by negative 80. So I'm going to have natural log absolute value 2,000 minus 80p is equal to, now here's where I get to make a choice. I can relabel these, or I can multiply everything by negative 80. I'm going to choose a relabel. I think I'm going to choose a relabel. So if I relabel these, both K1 and C1 are getting multiplied by negative 80. They're just constants. So is that not what I should do? I don't have to do that. Let's not do that. I'll just multiply both sides by negative 80. That's totally fine. And then I'll have KT plus C. That's also totally fine.
What if
Yeah.
I only multiply the AP with the KT, not with the C stuff?
That's fine, because essentially what you've done is relabeled your C,
Yeah.
right? So
Okay.
it's totally fine to have negative 80 KT plus a constant. We should just do something to indicate that these are not the same constant. So I'm just gonna throw a little subscript over there. So now they're not the same constant because technically we're multiplying both sides by 80. Okay. Now I can do e to the stuff on both sides. And I would have absolute value of 2000 minus 80p is equal to e to the negative 80 kt plus that constant. But I'm going to do the thing where I rewrite that as e to the c. And then I'm going to give this a subscript of C2 because I'm going to call this whole thing a new constant. And I'll have 2000 minus 80p. And that lets me drop the absolute value because that constant is going to suck up whether it needs to be positive or negative. Since I'm trying to get the p by itself, I'm actually going to add the 80p to the other side and subtract this one over so that I have 2000 minus CE to the negative 80 KT is equal to 80p. And then I can divide both sides by 80. And if I want, I can write that as 2000 divided by 80 minus, cool, I'm going to call that C3. Suck that up into one new C. Now this time, I ended up with more than one constant to solve for. So I ended up with both a C and a K. And if I'm going to solve for both C and K, I'm going to need two pieces of information. So it's not enough to just have a single initial condition. I need more information than that to find the specific solution. And luckily I have given us two pieces of information in part B because I have told us that the initial price is $15. So when t is equal to 0, our price is $15. And after 1 month, our price is $20. I just made up all the numbers in this problem. So I have no idea how gross this gets. Do we want to work through the algebra, or is it enough to say we could solve this system of equations if I was able to plug those things in?